We can call this chapter the second law of thermodynamics or entropy. We're going to do three basic things in this chapter. One, I'm going to state that you already know the second law of thermodynamics. Two, I'm going to find a state variable from heat, since heat is not an exact differential and is not a state variable. And then I will do an application to show you that the entropy of a closed system must increase or stay the same. So for the second law of thermodynamics, let's go ahead and put down second law, since that's important for our discussion. Second law, and we'll say thermo for thermodynamics. Heat flows from hot to cold. That's basically the second law. In other words, this is spontaneously. We're talking about natural occurrence in nature. Heat will naturally flow from hot to cold. It will not go from cold to hot spontaneously. So if you put an ice cube on the table, the heat will flow into the ice cube from the warm room. If you had heat going from the ice cube to the air, then the air would get warmer and the ice cube would get colder. So if the heat went from the ice cube to the room, the ice cube would never melt. And we know that's not true. So if you want to remove heat from a cold source to take it to a warm source, you need a motor or something, you need a refrigerator, something like that, where you're using work to extract heat from the refrigerator to the outside room. All right, but let's go back and review here the first law before we get into the second law. So the first law of thermodynamics, the first law states that the change in energy is equal to the heat that flows in to the system, minus the work that the system does. And we'll be looking at an ideal gas in this chapter also. So the work done when the gas expands is equal to the pressure times the change in the volume. So we can write the first law of thermodynamics as delta U equals Q minus P delta V. Now, P delta V, that combination, which is our work, is path dependent. So work is not a state variable. You can't say that the gas has some work content. And the same thing with heat. We can't say that there's a heat function of temperature in the gas. I would like to, though, replace Q with state variables, even though the combination will not be a state variable. Like here, the combination is not a state variable, but at least I have the work expressed in terms of state variables. So let's isolate Q on the left side of the equation and write that as delta U plus P delta V. I would like the left-hand side to be transformed into a state variable. That means the combination over here, which is not a state variable because that's the heat, I want to change it. So I'll have to do something here, divide both sides by something or multiply both sides by something to do that. So now let's look at the simplest gas, the monatomic gas. And in the monatomic gas, the energy is equal to 3/2 times the number of particles in the gas times kT. Now, we also have done in the past to show that this is also equal to 3/2. If you pick the number of moles, then the Boltzmann constant gets replaced by the ideal gas constant. And in atmospheric science, we put a star on there because we reserve R to be R star over the molar mass of the gas. So in that case, the R in our course is dependent upon the gas, while in chemistry, the R star is the ideal gas constant, is not dependent on the gas. So R star is R times M. And if we come in here and replace that, we'll have 3/2 N times, I'll put the M first, MRT. Now the number of moles times the molar mass is the mass of the gas. And we have looked at this before. So this is just a quick review to have this class as contained as possible with as much basic things in there. So we review some things as we go. Another neat thing to remember is that the number of moles times R star is equal to M times R, the mass of the gas times R. So I kind of like to have that equation written down, emphasized here, NR star. NR star is equal to MR. That helps me go between moles of the gas, number of moles of the gas, and the mass of the gas. Remember, in meteorology, we like to talk about the mass of the gas. So we can write then for the energy of the gas, 3/2 M RT. And our specific heat at constant volume, we have shown to be 1 over the mass times the derivative of the energy with respect to the temperature. And when we do that, what we will get is 3/2 R. The derivative of the energy with respect to T will pull off the 3/2 MR and be divided by the M. We'll have 3/2 R. Then remember in the past we talked about degrees of freedom. If we extend the monatomic gas to a diatomic gas, where we can have rotation and vibration and things, we replace the 3. That 3 got replaced with an F for the number of degrees of freedom. And with the monatomic gas, there's 3. Translational motion, kinetic energy in the X, Y, and Z direction. So notice that we can write the energy U, since 3/2 R is CV, I'm going to write this as, well, the M is going to be there. And then the 3/2 R is going to be CV, the specific heat at constant volume, and then there's going to be the temperature. Now I like this formula because this CV can be generalized easily with that F. So in general, we wouldn't have for CV 3/2 R, we'd have the F. But you don't see any 3's here or anything, so this is kind of a nice general formula to look at. So I'll go ahead and box that one off. Okay, so let's go back to our aim here. Our aim is to take this heat and to see if we can get on the left-hand side some exact differential appearing in some way. All right, so we can write the Q using delta U is going to be M specific heat at constant volume delta T, by taking the delta of both sides of this equation. And then we have plus the pressure times delta V. Now, can we express that Q in terms of state variables? That's what we're trying to do, because remember, for the work, we were able to express work in terms of state variables P delta V, even though when you integrate that, you find that's path dependent. So to help me out here, I'm going to write the pressure in terms of the volume and the temperature. All right. So remember the ideal gas law, the pressure times the volume is equal to N R star T. But now I'd like to use the rule that we just looked at, that N R star can be replaced by the mass of the gas times R from over here. So that means the pressure can be written as mRT divided by the volume. Now I want to put that pressure into this P. So that'll give me Q is M, specific heat at constant volume, M is the mass of the gas, times delta T. And now over here I'll have plus, I'll have M, R, T, and I'll have delta V divided by V. Now see that delta V divided by V, that would be really good, path independent, if we didn't have that T there. That T is what's messing us up, because you can integrate, think of this as a dV over V, and if you integrate that, you're going to get here a logarithm of V, and evaluate it at, say, V1 and V2, and that's going to be path independent. Just depends on the initial point and the final point. So this suggests that I divide by T. If I divide both sides by T to get Q over T, I will get M, the mass of the gas, times the specific heat at constant volume, delta T over T, and this is now the remarkable thing, because I did not mess up the first term. By dividing by T, this term is still going to be path independent. Just like delta T is path independent, if I integrate dt from 1 to 2, I'm going to get the second temperature minus the first temperature. Path independent, doesn't matter which way I go. All right, so then I'll have over here mR delta V over V, and I have solved my problem. Because this combination is an exact differential. And we can then call this with the delta, I'm going to call that delta S. S is going to be the entropy. All right, but for now, just consider it delta S. So delta S equals M CV delta T over T plus MR delta V over V. And now I can integrate this. I can make it a differential, because it's an exact differential. So I can make this a ds, differential S, is M CV dt over T plus MR dV over V, and now I can integrate both sides, and the result is independent of the path. So let's do that. We go from S1 to S2 ds, and then we'll have M C sub B, and we're going to integrate this from T1 to T2. All right, that's dt over T. And then we'll integrate this one from V1 to V2 of dV over V. And remember, all of our processes are idealized where there's equilibrium state at every point in time. And what that means is that there is a well-defined temperature everywhere in the gas. There's a well-defined volume and well-defined pressure and well-defined S, whatever that is. All right, it's going to be the entropy. So this is going to give us here, integrate the S, going to go from S1 to S2. And here we're going to get logarithms. We're going to get the log of T from T1 to T2 plus MR and the log of V from V1 to V2. Now, you might remember from math class that you can't take a log of something that has feet or meters or cubic centimeters. So when we write this out, everything's going to get fixed, because we're going to have here the log of T2 minus the log of T1. And this has meaning when we combine them. And we'll have the ratio T2 over T1 because this is the log, see, of T2 divided by T1, and everything works out. So don't let that bother you that at this intermediate step, you see something like the log, well here we'll see the log of V2 minus the log of V1. These are going to get combined and everything's going to be fine. The log of V2 over V1. All right, so you can think of this as a ratio. And this over here is S2 minus S1. Now I like to come up here and write that equation. Now to have the equation up here. This is a very, very nice equation. So let's call that delta S. And we can write that as the Q over T, going back to what we had originally. And since this is an exact differential, I could write differential, see, of this S parameter. Now over here, I can't do that with the Q. I have to use my delta symbol, which indicates as a reminder that we do not have an exact differential. The delta Q means that Q, that heat, depends on the path. But if I divide by the temperature, it doesn't, because I have an exact differential. So remember how we get our little s. Our little s is we divide the s by the mass. So we can get this equation here and have ds, where that's the little s, is equal to the differential of the big S, and then divide by the mass. That's per unit mass. And if I do that, then over here I would have little q divided by T. So I would like to call this equation 17, where we have the d little s is equal to the infinitesimal heat transfer divided by the temperature. And remember, we're going for about 33 or so equations that are basic by way of review of thermodynamics, which we will use in deriving the adiabatic lapse rate formula, the general one. Now what I would like to do is, I would like to show you that when heat flows from hot to cold, I'm going to do a simple example and show you that means the entropy is going to increase. So for this problem, we're going to have a reservoir, like a lake, and put a small volume of gas inside the lake. All right. So here, this gas will have T1. All right, that's going to be the gas in there. So we're going to say here we have a gas. And this here is a reservoir. Then that reservoir, we can think of that as a reservoir lake. And this is going to have temperature 2. Now here, the heat of temperature 2 is going to be greater than temperature 1. So the heat is going to flow into the gas, and it's going to bring that temperature 1 up until temperature 2. And here we're going to assume that all states in doing this, there's an equilibrium state. See, what would happen in real life is that it would get a little bit warmer here. It wouldn't be the same temperature everywhere in there, but we're going to assume that's done so slowly. And that's a very, very good trick that we use, because even if we put that in there in the lake and the heat flows in and we wait until the temperature is the same, we're replacing this real situation with ideal reservoir that's only a slightly different temperature than T1. And then we're going to make that temperature a little bit greater than the previous one. and keep doing that. And in that sense, by a series of swapping out reservoir lakes, we can have everything be done where there's an equilibrium state. That's ideal mathematics so that we can do our integrals, because you can't really integrate anything, temperature, pressure, anything, if say the pressure is not the same everywhere. Okay, so that being said, we're ready to do a calculation to see what this entropy is going to be. So we already have the formula. We have the change in entropy here. And this is going to be for the gas. And this was derived for ideal gas. So we have the relationship. We will just copy this down again. This is going to be mCV, the log of T2 over T1. But now, I'm not going to copy the second one down because I'm going to say here that there's no change in volume, right? This gas is in there in a container. So if there's no change in volume, then this term's gone because V1 equals V2 and the log of 1 is 0. All right, so that's what we're going to take. V2 equal to V1, and then the log of V2 over V1 is the log of 1, and that's going to be 0. So this is the change in entropy for the gas. Now what about the heat transfer into the gas? Well, we do have this other formula. Remember that the transfer of heat into the gas is equal to the mass of the gas times the specific heat at constant volume of the gas, since that's what we're dealing with here, times delta T. You might recall that your definition for heat capacity is you take the heat and divide by a delta T. And then if you divide this big C by M, you then get Q over M delta T. So all I did here is I took the Q and said, since this is the little c, and we're doing constant volume, so we could put a little v there and a little v there, and remind us that's a constant volume case, then this is saying that the Q is M delta T times CV. So that's kind of a neat little relationship. Why I need this is because I want to calculate the change in entropy for the lake. And I'm going to do that using the reverse. In other words, the negative sign. If the Q for the gas, what transferred into the gas was this one, then what happened for the reservoir, which is the lake, RES, that's going to be minus mCV delta T of the gas. So remember, for the gas, the change in temperature is, well, it's coming from T1 up to T2. So that's what the change is. And here I need to put a minus sign if I want to know what the heat is taking place for the reservoir. The reservoir is losing the heat transfer. I don't want to say it loses heat because it's not an equation of state. So I'll say that the heat transfer for the lake is negative. And when you add the heat transfer of the gas to the heat transfer of the lake, you get 0 because there's no net heat transfer in that case. They balance out. Now, the neat thing about the reservoir, and this is another subtle point, is that the change in entropy for the reservoir would be the heat transfer divided by the temperature, and for the reservoir it's constant, not changing. All right, the temperature of the reservoir stays the same because it's so large that we can neglect any change there. So that's going to give us minus mCV T2 minus T1 divided by T2. So now the change in entropy total, the total change in entropy would be the change in entropy of the gas plus the change in entropy of the reservoir. So now we need to combine both of these. Well, for the gas, we have m c sub v, the log of T2 over T1 from here. Then for the reservoir, we have this. Then there's a minus sign there. So this will be minus m CV. And we'll have then T2 minus T1 over T2. All right, and that's the total change in entropy of the system, and closed system here. Now I want to show you something remarkable. I want to show you that this is going to be greater than 0. It's going to increase the total. No matter if T2 is greater than T1 or T1 is greater than T2 and the heat flows the other way. This is amazing. So no matter which way it goes, the entropy is going to increase. The only thing that's going to be, say, the 0 case is going to be if T1 equals T2 and they're all at the same temperature. Both are at the same temperature when we start, so there is no heat transfer because the log of 1 would be 0 and T2 minus T1, if they're the same, is 0. So, but if they're not starting out the same, then it doesn't matter which is which. Now, in my text that goes at this lecture, I have a graph. But I want to do something, I think, which is very insightful here, is to do it and analyze the function, and to show that the function is always going to be greater than 0, except for the case where the t's are the same. So to do that, what I'm going to do is I'm going to let T2 over T1 be x. So let here x equal T2 over T1. And then, because I don't want to keep writing this mCV down, I'm going to consider the change in total entropy divided by mCV, since these are positive in the denominator. So if this is always greater than 0, so will the delta S be always greater than 0. So this is going to be equal then. I have this nice little math form function, T2 over T1, and then this is then a minus sign, T2 minus T1 over T2. All right. So when I translate this to x, I can focus on a function f of x, which is going to be the natural log of x minus, and then here what I'm going to do is I'm going to write this as divide out 1, subtract T1 over T2, and this is T1 over T2 is 1 over x. So this would be that minus sign, and then this would be a minus 1, and then that minus sign with this minus sign be a plus sign. And since this is T1 over T2, the flip, I'm going to have 1 over x. So I can focus on this equation. I can concentrate on this equation. And also I notice that the temperatures are positive. So that means the ratio is going to be positive. So I also have the condition that x is greater than 0. And I can focus on pure math. That's what I want to do here. Focus on this function when x is greater than 0. And I want to show you that, see, when the temperature T1 is less than T2, that's how we set the problem up. And in that case, x will be greater than 1. But if you have x less than 1, that's the case where the T1 temperature is greater than the T2 temperature. And I want to show you that it doesn't matter what x is, this is always going to be positive. All right. And I think this is very profound. All we're using is that heat flows from the hot to the cold, how I set this problem up. And then no matter which way it goes, I'm showing you the entropy always increases. This helps me understand entropy like nothing else, at least. But there's so many formulations of entropy. There's more than one path to the truth. So, but this is my favorite. Okay, so here I'm gonna do a little graph here. So we have here x We go x here, and let's say we have 1, 2, 3, like this. And this is f of x. And what I like about this is that there's a nice analysis with mathematics and algebra and calculus. The first thing we can do is let's calculate the slope. So the derivative gives you the slope. The derivative of the log of x is 1 over x. The derivative of minus 1 is 0. And the derivative of 1 over x is minus 1 over x squared. Remember, for x to the minus 1, take the derivative, you pull the minus 1 down, and then you subtract 1 on the exponent. And that's what we have here. And let's go ahead and write this out. So we have x squared in the denominator, and then we have here x minus 1. Now, if x equals to 1, we have no slope. And that's how we do max-min problem in calculus. So that means here we have no slope when x equals to 1. And when x equals to 1, what do we have? Well, log of 1 is 0. We have minus 1 plus 1 over 1. We get 0. So here is a point. And I want to show you that that's the minimum. And the way you can show that that's the minimum, you can do it a couple of ways. You could show that the function is going to be positive everywhere. But I want to go ahead and do the standard choice where you take the second derivative. And the second derivative here is, the second derivative would be this first 1 over x would become minus 1 over x squared. And this here would be a plus 2 over x cubed. So we're doing here x to the minus 2. You take the derivative, the minus 2 comes down, and you have x to the minus 3. So that's what we have here, the 2 and 1 over x cubed. And that minus sign there, cancel that minus sign to get you a plus sign. And when we took the derivative of 1 over x, we get introduce the minus sign, 1 over x squared. So that's equal to, we divide it by x cubed. This is going to be, I'm going to put this term first, the positive one, 2 over x cubed, and then here I'll have a minus x, so x over x cubed is 1 over x squared. So what this is saying, at this point 1, this has given us a 2 minus 1 over 1 cubed. This is a positive quantity. So since that's positive, remember when you take the second derivative, that means you hold water, and that means we have a minimum. All right. But now notice here with this slope, if x is less than 1, this slope is always negative. And if x is greater than 1, it's always positive. So what's happening here, if you look at the negative slope here, it's going to be always negative. And in fact, it starts off where you have 1 over a small quantity. You're going to have 1 over a small quantity is going to get you a big quantity. So the slope is very, very steep and negative, sliding downhill. And then we get here, it starts to go up like this. Second derivative gives you the change in the slope. So here, the change in the slope when x is less than 1, actually a change in the slope here is positive, which means that it's getting less negative, it's getting more positive, and that actually keeps going until you get to 2. So I'm going to stop right there at 2, because this says here, from x equals 0 to x equals less than 2, here less than 2, that this second derivative is positive. So the second derivative means its first derivative is always increasing. The slope is increasing. So we could write that down as saying slope increasing, and we could then give an interval. We could say from 0 to 2. And when you put parentheses, it means you're not including 0, you're not including 2. An open interval. And then the slope, when you get more than 2, is the slope is actually then decreasing. And that's going from the interval, open interval 2 to infinity. So that means this has to turn the other way. It has to turn, and it's going to become, instead of concave, it's going to become convex. Isn't that wild? All right. So this is a nice, rich mathematical analysis to see what's going on. And this, remember, is our entropy. That's the measure of the entropy, the F. And look at this. It's always positive. Everywhere. No matter which way the heat's going. Well, it's going to have to go from hot to cold. But in the case where it's going from lake to gas, because the lake is hotter, that's going to be an increase in entropy. And if it's going from the hot gas out to the lake, that's going to be increased entropy. That is amazing. So it's easy for me to believe the entropy always increases no matter what the problem is, since in this simple case where I can analyze everything, the heat can flow in either direction and the entropy still increases. Only stays the same when the temperatures start out at the same temperature. That is awesome. As the change in entropy in a closed system, because you remember the entropy change individually here for the gas and the lake can do positive and negative things, but the closed system, adding them both together, that's going to be greater than or equal to 0 for a closed system. Second law of thermodynamics. And what I really love about this approach is that we only had to assume that the heat goes from hot to cold, and then we just did regular physics, all the other, first law of thermodynamics, and this basic stuff that we did, and came to this conclusion. Now, historically, there's been two famous statements of the law of thermodynamics. Statement 1, known as the Clausius statement, says that it is impossible for a self-acting machine working in a cyclic process unaided by any external agency to convey heat from a body at lower temperature to one at a higher temperature. So I like these little diagrams that we can make to illustrate this. Let's say here is a reservoir at the hot temperature, and here is a reservoir at the cold temperature. And what can happen is you have some kind of like engine here or some kind of machine, and we can't have the effect, the net effect of having heat be transferred, say this is Q, from the cold temperature, the cold reservoir, to the hot reservoir. Well, let's figure out what the entropy is. Now remember, our entropy definition, delta S, is the heat transfer divided by that temperature T. So what we're going to do with the cyclic process, we'll just say, we'll sum over the cycle of the Q over T. Well, what do we have here? Well, we have here heat that's being given up by the reservoir down there. So that's going to be minus Q over T cold. And then up here, this reservoir is gaining Q. So that's going to be Q over T hot. Right. But T hot is greater than T cold. So I'm going to say but. And if that's the case, then if I write this equation out a little differently here, I'll have Q, factor the Q out. I have 1 over T hot minus 1 over T cold. So if T hot is greater than T cold, then this is going to be smaller than this term. And that means when we do that, you're going to have something less than 0. But that violates the second law of thermodynamics, which says for a closed system, the delta S has to be greater than or equal to 0. So that's one statement. And we pretty much already know this from our example here. So I think these statements historically are easier to understand now. Statement 2 is attributed here to Kelvin and Planck. It's called the Kelvin-Planck statement. Kelvin made it in the 1850s or so, and then Planck kind of reworded it slightly there. And Clausius did his in the 1850s also. So here, what it says, it's impossible for a device working in a cyclic process to extract heat from a single reservoir and convert it totally to work. All right, so let's go ahead and have this reservoir here at the hot temperature taking some heat, and we're going to let the heat go out here as work. All right, this is going to come out here as work. And here, we'll just put another reservoir down there, which we won't really need. So for this, the entropy change, when we do the sum of the Q over T, we just have one. It's going to be, this reservoir is going to lose that heat as the heat's transferred out. So this is going to be equal to minus Q over T H. But see, that's less than 0. You can't have that. So therefore, this is a violation of the second law of thermodynamics. Now, what does work? Well, what does work, if we have here the hot reservoir, TH, and we have here the cold reservoir, we can have, I'll just go ahead and do it like this. We can have some of this heat energy go into work and some be expelled. All right, so in other words, the QH is the heat transfer from the top reservoir, and then here going this way, this is Q sub C, that's being dumped in the environment. That you can have. So this is very fascinating, the way these diagrams go. You can put a circle there if you want, like I had a circle there and a circle there. So you can have this case where the heat transfer, QH, goes into work plus some heat that's dumped. So you can have that. All right. Now we can state the first two laws of thermodynamics the way a colleague of mine liked to express them. And see, the first law of thermodynamics can be considered as the conservation of energy. That the change in energy of the system is the heat transfer going in minus the work done. That's conservation of energy. And we can rephrase that as there are no free lunches. That you get nothing for free. You can't get work for free. You can't get energy for free. Energy is transformed. But now the second law here, where you take this input, heat transfer, you got to dump some. Well, that means you can't break even. All right. So the first law is no free lunches. Second law, you can't break even. So I'll close my class with these two diagrams.